And the Venn diagram is just a way to kind of pictorially represent sets. VENN diagram, Venn diagram. All a Venn diagram is this. You start with a rectangle, that's your universal set. That's everything you're considering. So the rectangle contains everything. Then you put sets in here as ovals or circles. Book uses circles, but mine tend to be more of an oval. But yeah, the sets are then the circles, and you don't have to use circles. You can use other shapes, but most of the time they're circular. That's set A, and then we'll put other sets, and usually there's overlap of sets. So usually the circles overlap, interlock. So set B, maybe draw it in there, and so forth and so on. Okay, depending on the number of sets, different way they look. But that's a Venn diagram. Okay, so keep that in mind. We'll utilize that as we go along here. Okay. I guess technically, though, the first set operation, let's talk about the set operation called intersection of sets. It's denoted with, it's the arch, an arch-looking thing. Red, A intersect B. A intersection B is the set of elements A and B have in common. A intersect B is the set of elements A and B have in common. Pretty easy thing. Just this means the set of elements A and B have in common. So if A is, which ones do I want to do? Let's say A is even numbers 2, 4, 6, 8, and 10. And B is 1, 4, 5, 6, and 9. Okay? What's the A intersection B? Well, it's just what they have in common. What do these sets have in common? 4 is in both of them. 6 is in both of them. That's about it, isn't it? So A intersection B here would be the set 4, 6. So yeah, we put two sets together, we get a new set, and depending on the set operation here, depends on what you get for your set, but this is a new set. A intersection B is the set 4, 6. Okay? It's the intersection. There's also something known as union. The union of sets. And nicely, it's denoted with, looks like a U between them there, right? But this set is the set of elements, well, let's say it this way. The set of all elements in A combined with all the elements of B. In other words, we're just going to dump the two sets together. The union of two sets, we're going to take all the elements of A and just combine them all with the elements of B. Okay? So now back down here, same two sets here. What's our union? Well, instead of just looking what's overlapping, I'm just going to take all these elements, 2, 4, 6, 8, and 10. Let's just do it this way. So I take all the elements of A and then combine it with all the elements of B. So I just basically group those two together, put those all in one set. Now, what's wrong with that picture? Well, for one thing, they're out of order, and most of us like to put them in order, so let's put them in order. 1, 2, 4, it doesn't matter, but 1, 2, 4, 6, oh, I forgot 5, 6, 8, 9, and 10 is really probably the way we instead of writing it that way, but just want to do it that way just to make the point. I'm just putting everything together. Now, I don't have to, I can write them in order, and I don't have to do the repeats, right? I have 4 and 6 there twice, so I don't want to repeat those. Doesn't make it wrong, but no need to write them twice. So yeah, A union B is 1, 2, 4, 5, 6, 8, 9, and 10. It's just putting everything in A combined with everything in B, which, you know, if you think about the name there, union, you had the Union of States. That was all the states. The Union of States would be all the states put together, so it's all the states combined. Same idea. Whereas intersection, think about the intersection of two streets. What's the intersection of the streets? Well, it's what they have in common. It's the overlap is where the intersection is. So hopefully those are easy to, seems like those are usually pretty easy to keep straight. The other thing let me mention for maybe later on down the line is another kind of alternative definitions here for intersection and union. That's fine to remember it that way, but this may be also the way the book puts it, but let me write it up here this way too. A intersection B, it's a set of elements. The intersection is a set of elements in A and in B. Whereas A union B is the set of elements in A or in B. You see the slight difference there? The intersection, I use the and. The union, I use the or. Yeah, to be in the intersection, it has to be in both A and B, right? For the union, does it have to be in A and in B? No, it could be in A or it could be in B. It doesn't have to be in both. So that's why the word and means intersection and or means union. And that, like I said, that'll be more significant next time in our next lecture. But for now, I just wanted to mention it. And is intersection, or is union. Try to remember that. We'll review that later, but just wanted to make that point. And it has to be in both, so it's intersection or one or the other. Okay? All right. There is another set operation, though, and it's the difference of sets. And this is really the only one that kind of has the same symbol as we use in numbers, but we're talking sets, of course. It is the subtraction symbol for difference, right? That's our difference in numbers. It's a minus, but same thing in sets. However, it's a little different way of doing it. Here's the definition. It's A take away B, or A minus B. That's the way it's written. But here's what it is. A minus B, this is the set of elements in A that are not in B. set of elements, the set of elements in A minus B is a set of elements in A that are not in B. Okay, so for example, back to what was our other ones? It was 2, 4, 6, 8, and 10. Is that what we had for A? And then B was, what was B?
1, 4, 5, 6, 7.
1, 4, 5, 6, 9. Okay. A take away A minus B is 2, 8, and 10. I'll just do it right there for you, right? First of all, A minus B in this case is 2, 8, and 10. Do you see that? Because those are the elements of A, right, that are not in B. 2, 8, and 10 are in A, they're not in B. I don't include 4 and 6 because 4 and 6 are in B. I want this set to be, okay. So that's what it is. Here's the way, in practice, I like to show you how to do it. And, we can read this A minus B. I like to think of it this way. It's A take away B. In other words, start with A and then take out elements that are in B. That's kind of how we do this. So let's redo this problem. A minus B. So this is the set I start with. I'm going to start with A and take away from it. So I'm starting with A. So A is 2, 4, 6, 8, and 10. Now I'm going to take away from it. What do I take away from it? I take away anything there that's in this B. So I take away the B elements. What's here? Take away 4, take away 6. That's how this is working. I start with A and then I take out from it. Take out the 4 and 6 because those are in B. So I'll wind up with 2, 8, and 10. With me? Okay? Now, important point here. If I reverse that, do B minus A. Same set? It's not going to be the same set. You see that? Because this is B take away A. So I start with, in this case, what? B. 1, 4, 5, 6, and 9. So in this case, I start with B and take away from it. Now, while I'm at it, let me make this point. It's B take away A. So I am not ever going to get any elements other than what's in B. I start with B and then take away from it. So I'm not going to get anything other than what's in B. I'm only going to take away from it. So what am I going to take away here? I'm going to take away A, which A doesn't have a 1. It has a 4, so I'm going to take away it. Does it have a 5? A? No. Does it have a 6? Yes. So I take away it. Does it have a 9? A doesn't have a 9, so I leave it. So this case I wind up with 1, 5, and 9. B take away A is 1, 5, and 9. Now I said that earlier because a lot of people want to try to put in some extra things here. They want to try to put in the 2 and the 10 here. But I don't do that. It's B take away A. So I start with B, and I don't get any ever bigger than B. I just take away from it. So I don't add. There's no add here. It's take away, you see. If you put in 2 and 10, you have added. We don't want to add. We want to take away. Okay? All right. So it's just 1, 5. So that's the difference of sets. And we did notice we do get a different set if we switch them around. Now, that's not the case for intersection or union. If you think about that, go back to that, either one you want to, for these sets. Remember, let's just do write those back up. What was our intersection? It was 4 and 6, wasn't it? And the union was 1, 2, 4, 5, 6, 8, 9, and 10. Well, if I reverse those, instead of A intersection B, what's B intersection A? Well, it's what B and A have in common. What do B and A have in common? 4 and 6. If I do B union A, union is put all the things together, so I take everything in B, combine with everything in A. So I take everything here, combine it with everything there. What do I get? I get 1, 2, 4, 5, 6, 8, 9, and 10. B intersection A is the same as A intersection B. A union B is the same as B union A, or B union A is the same as A. Yeah. Reversing the order on the union doesn't change it. Reversing the order on the intersection doesn't change it. The only thing of the operations here that we've talked about that changes is the difference. If you reverse those, it changes it. But no, it doesn't matter. And if you remember, it's kind of the same way with addition and subtraction. Addition, if you add two numbers and you reverse them, does that change it? No. But if you subtract them, does it change it? Yes, it does. So it's kind of the same thing. Some operations you switch them, it doesn't matter. Some, do you remember what that's called? What property? If you can switch them and it doesn't change it, extra point. Commutative. It's the commutative property. Intersection and union are commutative. In other words, you can switch them around, it doesn't change it. Difference is not commutative. Okay, that's just extra bonus there. Okay. All right. Okay, well. Okay, let's go ahead and mention, go back to the Venn diagrams here real quick. Let's think about intersection and union in terms of the Venn diagram. Because what we'll do a lot more of this in just a second, is we'll shade Venn diagrams for certain sets. And okay, so we put the A and the B circles here. Okay, so if I told you to shade A intersection B, would that be easy? What is intersection? It's what they have in common, where they overlap. So what would I shade? Right here in the middle, right? If I told you to shade A union B. Well, let me do this with you. One way we can look at this Venn diagram is think of it kind of as a puzzle pieces. If I cut this up into puzzle pieces, there would be 4 pieces. I'd have the outside part, call it part 1. Then I'd have this kind of moon shape, part of A. Then I'd have this middle piece, and then I'd have the B shape of the moon of B. So which parts would I shade for A union B? Well, union means take everything in A, so I'd shade everything in A, which A includes the 3, doesn't it? And then I'd shade everything in B, so I would shade 3 and 4, because I already got 3 shaded. Yeah, A union B would be the 2, 3, and 4 parts, right? Everything in A combined with their, yeah, that's union. What about that? Well, that's the part in A, not in B. So I'd start with A and take away B. A is 3 and 4 here, but I'd take away B, so I'd be left with this moon part here, part 2. Yeah, the A minus B is the moon shape of part of A. And of course B minus A would be the same thing, but on the B side. One more. What would you shade for that? A, what does this mean? Complement? What's the complement? What's not in A? Yeah, it's not in A. So if I number these off again, what would I shade? Tell me what parts to shade. Well, on Venn diagrams, the complement's easy. Just cover up, we're doing A complement, so cover up A, and whatever you don't cover up should be shaded. So 1 and 4, 1 and 4. Okay. We'll come back to this in just a second. All right. Let's talk, though, a couple more. Because what we'll have on the homework problems is, we'll be doing intersections and unions and differences, but they'll be more complicated. So let's talk about a few of those. Let me write up here.